Okay, welcome, Alexandro, with your talk on opening safe SDV APIs for developers using WASM.
Hi, everyone. Thank you for joining the presentation. My name is Alex. I'm the CEO of a small company called OCX Automotive. My background is in engineering, mostly operating systems and compilers. Let's talk about the web. For 30 years, but mostly 25 years, the browser has been the main way of interacting with applications. Probably most of the developers today write software for the browser. If you think a little bit of what you do at home and you're doing your work, most of the applications that you access are in the browser. From this point of view, the browser can be seen as an operating system or as a platform for applications. Nobody else in the field has done a better job than having the necessity to run code fast in a super sandboxed environment. For 25 years, browser developers had to run arbitrary code because nobody knows what code a website will send, super fast, because it needs to be exactly like a local application. And by the way, it can't touch your computer. And starting 10 years ago, we need to touch your computer because we need to access the USB, or we need to access some files from your computer in a constrained manner, in a way. So when writing secure and sandboxed applications, I think we really need to look at the web. Now, the main programming language on the web is JavaScript. The problem with JavaScript is it's super hard to optimize. Browser developers went great lengths to build compilers for JavaScript. We have V8 and SpiderMonkey. But whatever they're trying to do, it's super, super hard to optimize the code. So from the web, we have WebAssembly. Because browser developers were not able to optimize that code, make it run faster. And just to imagine the kind of applications that you have, a normal web page, like let's say Gmail, probably has about 100,000 lines of code in JavaScript. It needs to be compiled on the fly and run. WebAssembly is a binary format, which was intended for the browser so that developers could run code super fast. The idea was, let's write code in C, probably, usually math and stuff that would be compute intensive, put it into a binary code which is called WebAssembly, which is super easy to optimize. The way this assembly language is written makes it super easy for compilers to optimize things and run it in a really safe way. WebAssembly is a binary standard, which is formally verifiable, which the standard says that you have to verify before executing. So every execution engine will run through your code, verify that it respects everything that WebAssembly states, and that there's no way it can get out of the sandbox. If you compare it to assembly language, most of you probably know assembly language. Imagine you have a processor which knows what a function is, which knows what an if is, and which cannot make arbitrary jumps. Because basically, that's the WebAssembly engine. But this code is super easy to optimize. You can call WebAssembly the compiled version of JavaScript. So we went from JavaScript to WebAssembly. This was all intended for the browser to run code super, super fast. And this was happening somewhere in 2017. Developers realized that, hey, this is a good idea. And actually, WebAssembly is not the first language that does this. Java did it in '95. Microsoft did it in '98. and others did it further along. The problem and the key difference is the following. Java has a bytecode, so binary code, which is proprietary. Of course, it's an open thing. But Oracle still owns the patent, and they can modify it as they wish, and somebody has to follow. Yes? Yes, but they still control the language. I mean, if Oracle says, hey, we need to implement this, people will have to follow. .NET, same problem. It was designed by Microsoft. Nice thing. Still, they control the language. Dalvik is what Google came up with, and for Android. Yes, you write programs in Java. No, they don't execute the JVM. They made a new language, binary language called Dalvik. It's, again, proprietary. They control it. And then there's JavaScript. JavaScript gets compiled and cached. I'm talking about V8 because it's the most commonly used engine outside of the browser. But again, it's proprietary. Google is contributing to V8. And yep, none of these are formally verified. When they designed the language, full sandboxing was not one of the priorities. For Java and for .NET, it was just to run it on every system so we can port applications. For Dalvik, it needs to run fast on Android. And for JavaScript, we need to be able to transform it in binary code super fast. WebAssembly, on the other hand, is an open standard. There's no single company behind driving this language. It's formally verified because they learned from whatever these others did. They had 20 years to learn about it. When it comes to security, Java, .NET, Dalvik, they filter things. They don't allow you to exit the sandbox, and I quote the sandbox. But Java and .NET were built for applications. They had the idea in mind that you need to access the computer's resources. It's an app running on your computer, and you know what you run. So they can filter things, but they filter it. Dalvik, the same thing. JavaScript and WebAssembly were not meant for normal applications. They were migrated from the browser. So when they in the browser, you have nothing. Everything is in the browser and needs to be in that environment. When they migrated outside, to the outside world, they needed a way to allow it to access the computer's resources, sorry. And there was capabilities. You either have that interface available, either you don't. So it's not that, OK, you have the interface, but we have a piece of software that verifies some permissions. No. If you can access something, that means you have the interface available. If you're not allowed to access it, for instance, I don't want it to access networking, I'm just not supplying a networking interface, which means that whatever the code does, it can't run that. So that's capability-based. And then we have data sharing. Data sharing, not among modules that are written in the same language, among modules written in different languages. The problem is Java, .NET, and Dalvik can all interact with the outside code through the C API, which is 40 years old. Great choice at the time, terrible choice today. Dalvik does no binder. It's Android specific. And for JavaScript, it's mostly hash maps. Any data structures, anything that you have in JavaScript turns into hash map, more or less. For WASM, we have the component model, which we will talk in a minute. Software engineering. So this is coming from the perspective of a software developer. Software engineering compared to normal engineering, like mechanical engineering or electrical engineering, is not great today. We need to go back to the drawing board. Our software pieces, like the binary files that we have, are super, super brittle. Imagine that we have two programming languages, and we are still not sure that they can interact. Imagine just Google is putting 1 million for interoperating with C++, Rust and C++. This should be trivial. It's not. They will need more than 1 million to make this happen. So in a way, what happens today in software engineering is we compile code and get components, which we need to connect somehow. But in mechanical engineering, this translates to, I have 2 mechanical pieces, I can connect them, but I need to know that the manufacturer that made the piece is the same. Otherwise, I might not be able to connect the mechanical things. Basically, we glue together pieces with duct tape. The C API is so brittle, and if we go to relocations and how libraries work, I'm super amazed it actually does work. I don't know if anybody has tried to do relocation and library linking. It's some magic that the operating system does, which probably a handful of people know how to do right, almost no documentation there. So it's super, super difficult. It's like connecting it with duct tape. We need a way to be able to build functional schematics of our software. Get pieces, put them in the schematics, connect them semantically, and make an application out of it. That's what every engineering field does. We have mechanical drawing boards, we have electrical schematics, but in software we don't have these ones. So, WASM on the road. In 2017, they defined WASM Core, which was built for the browser to run one single computational module in the browser fast. It could connect to the browser world with something that was like the C API. You could send numbers, floats, and that was it. I mean, anything else you had to improvise. It's when they came out of the browser with the WebAssembly modules, they defined WASI, WebAssembly System Interface. This is like POSIX for WebAssembly. And they designed a model which was very, very similar to the C API, which was using C strings, heap allocations, stack pointer, frame pointers to interact with the WebAssembly module. It's horrible. And people doing this realized that this is wrong. This is really the wrong way of doing it. So WASI never got into real production. WASI is called preview number 1, and it was dropped. We do have applications that use it, and it's usable, but it's not going to be the standard that people will use. So somewhere around 2020, the WebAssembly working group started defining WebAssembly components. WebAssembly components are like libraries for WebAssembly. It defines a standard of how data should be exchanged between WebAssembly modules. And it was modeled, surprise, from the Rust data model. It has enums with payload. It has the idea of sum and none. It has structures, lists, borrowing. You can borrow resources. You can own resources. And this is not surprising. The same group of people which contributed initially to Rust, was Mozilla mostly, is the same group of people which modeled the WebAssembly components model. You can share strings, numbers, enums, lists, tuples. You can borrow things. You can transfer ownership of things from one component to another. So it's like shareable libraries, but done in the 21st century, not 40 years ago. It's still a moving standard. So WebAssembly component is still being defined today. But we think this will be the new way of sharing application components or binary files. Let me just give you an example where they actually use this today. Rust we talked about Rust a few about Rust these days, has no ABI. So if you have a Rust module and Rust library and you want to link it into a Rust program, you can't link the binary code. You have to supply the source. There is absolutely no Rust ABI. A structure can be represented different from one minor version to another minor version of the compiler. So you need to see the source. But with WebAssembly components, you can always compile a Rust crate into WebAssembly component, which has a standard for sharing data, and then integrate the component into your software. So this is where it's being used today. In order to run WebAssembly, you need a WebAssembly engine. And there's tons of WebAssembly engines. The most known one is V8, because WebAssembly runs in the browser. Just a fun fact, VS Code, which probably you all know, has syntax highlighting written in WebAssembly. It's so slow to write it in JavaScript that they just used WebAssembly and wrote the syntax highlighting. So V8, the JavaScript engine in Chrome, is probably the most used WebAssembly engine. It's written in C++. It's present in Dino as well. Dino is Node written backwards. Same person that did Node did Dino. Afterwards, it supports the WebAssembly core modules, and you can run components in an emulated way. It doesn't support components out of the box, but you can shim it with some JavaScript. It JITs code, it compiles code ahead of time if necessary, works on all big platforms, so x86 and ARM, but needs an operating system. Definitely needs an operating system. It's going to be a mess in certification. There's no way that somebody can certify a compiler like V8. There's no way. The next engine is WASM time. WASM time is the reference WebAssembly engine for using WebAssembly outside the browser. It's developed for WebAssembly components. So it's written in Rust. It supports the core modules. It supports WebAssembly components out of the box. It JITs. It compiles ahead of time as well, so you can have a binary, runs on big platforms like x86 and ARM, and does need an operating system. And again, no way it can be certified for safety critical because it generates code on the fly. WASMer, also written in Rust, does not support WebAssembly components. Same story, not certifiable because it JITs code, and there's no way it can do it any other way. WebAssembly micro runtime is again written by the same group as WASM time. It's written in pure C, super embeddable. It's super, super small. Runs core libraries, doesn't know WebAssembly components so far. Does have a JIT, so you can opt for it to JIT or to compile ahead of time, but it can also interpret. Runs on everything. It's 50 kilos. The engine is 50 kilo. We ran it on Arduinos. And probably with some work, it would be certifiable. And there's a long, long list of WebAssembly engines. One that we are working on is WebAssembly Interpreter. I'll talk a little bit more about it later. It runs core modules, and our significant contribution will be components. It doesn't JIT. It doesn't compile ahead of time. It runs on any platform, and we will make it certifiable. The goal of it is to be able to safety certify this. It's written in Rust. To give you an idea on how this WebAssembly concept can be used, I'll try to go through an example. So let's say we want to build a new car, and we want to open up some APIs for third-party developers. First requirement is it needs to be super sandboxed. Third-party applications can be anything. It cannot interfere with the running of the car, can't interfere with safety functions on the car, can't render the car useless, and should not be able to steal data. So the first thing that we will do is define a few interfaces which these third-party modules will be able to use. If you're familiar with interface languages, it's WebAssembly components define a set of defines an IDL, interface definition language, where you can define the interfaces and what the functions are and what the data models are. It's similar to AIDL of Android. If you know Android, you know AIDL. Again, it's a standard. It's not like AIDL that one company decides how this looks like, and then it evolves like the company wants. So in this example, we defined some interfaces like CAN, file system, digital input-output. These interfaces are versioned, actually semantically versioned, and we can publish the interfaces into an interfaces registry. The second step is we need to define an ECU on which these third-party applications will run. These third-party applications are super sandboxed. Their world will be exactly what we allow them to see. They will never know the hardware on which they run. They will never know anything about the operating system. They will just know they have an ECU, which is fully virtualized. So using the interfaces that we previously defined, we can define a virtual ECU and allow this ECU to tap some of the buses in the car, or some of the functions of the car. For instance, read the CAN, read non-volatile storage, and others. After defining a virtual ECU, we will define a configuration. So we added the interfaces to the virtual ECU. These are the interfaces that components in that ECU can use. Now we need to connect those interfaces to the actual car. So the NVM, if it's a Linux system, will be connected to some file system driver probably. The CAN interface will be connected to a CAN bus, one of the CAN buses. And then if you have semantic interfaces like doors, those will be connected to either a CAN interface, either to a digital interface, depends on how the car works. So once we have defined a virtual ECU which defines which are the interfaces that third-party components can access, we have to have a configuration to connect it to the actual operating system of the device where this is running. For the same virtual ECU, a car manufacturer can define several configurations depending on which device that software will run. If it runs on the infotainment, probably it will be one configuration. If it runs in the instrument cluster, it will be a different configuration, depending on the operating system and the buses that it has. Lastly, third-party developers develop components. They don't even have to develop the whole software. They can develop a crypto component, data processing component, something that does something. The component imports interfaces and exports interfaces. And then an architect can pick out components from a repository, connect the components exactly like you would do a schematic, an electrical schematic, where you connect chips, you connect components, and deploy the app. The app is a set of components that work together, share data through standard interfaces, and run into a fully virtualized environment. The beauty of this is this can run in the car, and it will run exactly in the same way in a cloud or in a testing environment. Components, because they import and export standard interfaces, can be tested alone or together. As long as we build a test bench that exports and imports the interfaces that the components need, we can test them in any environment. These components are binary code. They're not platform binary code, but they're binary code. It's not source code. It doesn't, because the interfaces are standard, it doesn't matter. The programming language doesn't matter. We have written components in C, C++, Zig, Rust, JavaScript, Python, for JavaScript and Python, the component simply contains a small JavaScript engine or a small Python engine inside the component. So it really doesn't matter. The language doesn't matter. Nobody cares about this. And an application can be composed out of several components written in many programming languages in the same way. Once the third-party developer publishes the application, it's the OEM's job to deploy it to the car. That can be done in any possible way. Every OEM will have a different method of transferring the data to the car. That is something that is OEM dependent. Moreover, you can have several versions of the component on the car because you have several drawings of the application. An application can be updated on a component level. You can swap out a component and put another component, another version of the component. All the other application components stay the same. A few words about certification. So WebAssembly has a big downside. Big WebAssembly runtimes are super hard to certify. They use compilers in the backend. They generate code on the fly. And for instance, for aerospace, you will never be able to use this. For aerospace, you need to verify the binary code. Well, if I use a WebAssembly engine that does code on the fly, I don't know the binary code. So what we are trying to do in an effort with DLR, DLR is German's NASA, is to build a certifiable execution engine that runs on really small chips, so it's stackless and runs with Rust, no STD, and can scale up to larger chips. DLR's goal is to work with WASM core. Our goal is to add the components model to it and be able to write it in such a way that it's ISO 262 certifiable for ASIL D, out of context. The project is open source. I forgot to put a link here, but I'll gladly send the link. It's called WebAssembly Interpreter, WASM Interpreter. You can search it out on GitHub. It's mostly done, so hopefully we'll be able to start the certification process soon. All right, so this was my presentation. I know it was a little bit technical. Me being from a compiler background, this is super familiar to me, but I'll be happy to answer any questions.
Thank you. For the presentation about components, consider I have 3 JavaScript components, and each will come with own small JavaScript engine, yes?
Most probably, yes. I mean, it depends on, you have to have binary code that executes. Now, probably you will have to have a small engine, but you can have Jerry script, which is like 60K, maybe 60K.
But still, with every component with our own garbage collection, yeah, memory allocation, and so on.
Yes, it needs to do this.
The same if I have like C, C++, and Rust component, I want to write 3, and I need allocate memory and run threads. Every component will do in own way with own memory, like or is it?
No, this is handled by the engine. I mean, threads. It's in the proposal for WebAssembly components. So threads will be, you will have a WebAssembly instruction for a thread, and that's going to be handled by the engine, because you can't make a thread.
And memory allocation?
Memory allocation, for data that is inside the component, you need to handle your own memory allocation. For data that you share, that's not up to you. That's up to the execution engine.
And it means that every component has own address space, or they share one?
It's like this. So components are composed out of one component is composed out of several modules. Modules in the same components share the same linear memory. But modules communicate with each other through the component API. So technically, you can define several modules which are built independently, put them into a single component, communicate through interfaces, and have the same memory.
Inside components, no problem. I mean that between components.
Between components, this is the rule. I mean, if you have two separate components running, usually that would be the equivalent of two processes. And they copy data in between. Now, if they actually copy data or the WebAssembly execution engine does zero copy, that's a different story.
Okay,
I think I was not very clear. So the WebAssembly component model defines the idea of having semantic interfaces. The actual component is a process, will be the equivalent of the process. But inside the process, inside the component, you have several modules. You are building the modules, publishing the modules to the registry, and when you need to run an app, the app is actually the component, which is formed out of several modules.
Still, if component is a process, it needs to ask somebody about memory, give me memory, this is your memory back, and so on and so forth. Okay.
Every WASM application, let's call them applications, has its own linear memory. That is supplied by the execution engine, and it's its own memory. For the application, it seems like a linear memory. For the execution engine, it depends on how it can do this.
And you also mentioned language. Let's draw like diagrams. Is like it was some attempt. Like UML works quite well, explains object-oriented software. Are there any languages which can be used to draw really like some standards or something, or at least on the same level as UML?
I don't agree necessarily about that. So I see it in this way. So you have UML, but UML is a paper. You, the developer, have to obey the UML. In the case of WebAssembly components, the component inside, or the module, let's call it the module. Each module inside describes its own interface. So if you can easily make a piece of software where you load these modules, it reads their interfaces, you can connect them, hit a button, and get a new piece of software, which is the composed version. So in UML, you look at the UML, and then you need to obey it in code. Here, you do it. I mean, the schematics is not a paper, it's a software.
But we are like speaking about like drawing something. Drawing means drawing. Otherwise, like if of course we're on code level, it's clear. Yeah, code level is code. That I thought about that it will be some way to draw really like see interfaces, like make sure they're connectable and so like create scheme and then like deploy with one press. Nice idea, like already like implemented even in Corba components like 25 years ago or something. So.
So and so. We've not, considering how software is done today and how it looks like, I think we have not been very successful, my personal opinion. But personal opinion, that was not very successful. Yes?
So how do you deal with priorities for threads? So, I mean, if you're putting in a car, there's a lot of real-time jobs that need to be done there. Without some concept of priority in the application, it's kind of...
I assume you have the engine that runs in a priority thread which executes the component.
So you can't mix priorities at all?
The thread interface is being defined at the moment, but not really. But considering that this is useful probably now for third-party apps, that should not be a problem. But again, you can have a operating system thread that has a high priority, which runs the code but doesn't run binary code directly.
Yeah, okay, but usually in a real-time system, you give different priorities to different tasks based on their period, and you couldn't do that.
I think you could, but let's talk this offline.
Thank you.
Thank you.